Hey guys, so in this video we're going to introduce the idea of an ice chart and discuss the situations where they should be used. So an ice chart is a mathematical table that is used to find equilibrium concentration expressions for all of the species involved in a chemical equilibrium. Remember that the abbreviation ICE actually stands for Initial Change and Equilibrium. We know that the equilibrium constant can be expressed in two forms, Kc or Kp, and determined by the equilibrium concentration or partial pressures of the reactants and products respectively. Often, chemists know the initial reactant concentrations in a reaction and the respective equilibrium constant, but want to solve for the equilibrium concentration of the products and reactants. Ultimately, in order to know the equilibrium concentration, we must mathematically solve for the change in the initial concentrations, which is designated with the variable x. So to understand how to set up an ice chart, it is best to start with a generic example. If we consider the reaction 1 mole of gaseous reactant A in equilibrium with 2 moles of gaseous product B, we would most likely be given the initial concentration of our reactant A in the problem, and we would know that the initial concentration of product B is 0 because that would be the concentration of the product before any reaction had started unless otherwise stated in the problem. The change in concentration is going to be based on some factor of x. Now, as long as our initial concentration of our product is 0, that means that Q is going to be smaller than the value of K, meaning that the forward reaction is proceeding. So the change in the concentration of our reactant A is going to be a negative factor of X, and that factor is dependent on the coefficient in front of the reactant in the balanced equation. So for this reactant A, we only have 1 mole, so that means we're just going to be subtracting X. But for our product B, since we're forming our product in the forward reaction, we're going to be adding some factor of x, which in this case is going to be 2x because the coefficient in the balanced equation is 2 in front of the B. And from this information of the initial concentration and the change in the concentration, we have a mathematical expression that represents the equilibrium concentration of the reactants and products. So the equilibrium concentration of our reactant A is going to be equal to the initial concentration minus the change, and the equilibrium concentration of product B is going to be the initial concentration 0 plus the change, so ultimately just 2x. Now we know that the equilibrium constant Kc is equivalent to the law of mass action for the reaction. So therefore, for this example, it is equal to the equilibrium concentration of the product B squared over the equilibrium concentration from reactant A. From the ice chart, we have obtained the mathematical expressions equivalent to A and B's equilibrium concentrations. So if we plug these into the expression for the law of mass action, since Kc and the initial concentrations of the reactant A would be known, so we would know Kc and the initial reactant concentration, then we could solve for the value of x. But in order to solve for this value of x, we would need to rearrange the expression into its quadratic form. So in general, a quadratic equation reads ax squared plus bx plus c is equal to 0, where a, b, and c are the coefficients for the respective terms of x squared, x, and then having no variable x. So at this point, we can use the quadratic formula to solve for x. So if you remember, the quadratic formula is equal to x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, solving for x using the quadratic formula can sometimes be time consuming, so it's important to write out your steps so that you don't make any errors when you're solving. However, in some situations, we don't need to solve using the quadratic formula. When the equilibrium constant for the reaction is very small, we can assume that the value of x is negligible compared to the initial concentration of reactant. This approximation is called the x is small approximation. If you use the x is small approximation, you must verify that x is negligible. So this is going to be true if the value of x is less than 5% of the initial reactant concentration. So mathematically, we would verify this by saying the value of x over the initial reactant concentration times 100. And if we get a value that's less than 5, then this x is small approximation has been verified. So now let's go over some examples using ice charts to solve for equilibrium concentrations of reactants and products. So let's consider the reaction where N2 gas plus O2 gas forms 2NO gas and Kc is equal to 0.10. The reaction mixture above initially contains a concentration of N2 equal to 0.200 molarity and a concentration of O2 equal to 0.200 molarity. We're asked to find the equilibrium concentrations of the reactants and products at this temperature. So we're going to do this using an ice chart. We know the initial concentration of N2 is 0.200. Initial concentration of O2 is also 0.200. We're not given a concentration of NO gas, so we're going to assume it to be 0, meaning that Q is equal to 0, and therefore the forward reaction proceeds because Q is less than K. Now we must determine the change in the concentration of the reactants and products in order for the reaction to get to equilibrium. So remember, the forward reaction is proceeding, so that means the reactants are going to be decreasing by some factor of x, while the products are going to be increasing by some factor of x. And that factor depends on the coefficients from the balanced equation. So both N2 and O2 just have a coefficient of 1, so we're just going to be simply subtracting x for both of those reactants. But for our product, NO, we have a coefficient of 2, so that means we're going to be adding 2x in order for the concentration to get to its equilibrium concentration. So now we can solve for the mathematical expression that is equivalent to the equilibrium concentrations of the reactants and products. So the equilibrium concentration of N2 is going to be equal to 0.200 molarity minus x. The equilibrium concentration of O2 is also going to be equal to 0.200 minus x. And the equilibrium concentration of NO is going to be equal to 2x. Now in this situation, Kc is not a small enough value in order to use the x is small approximation, so we are going to need to solve using the quadratic formula. So we know that our equilibrium constant Kc is going to be equal to products over reactants raised to their respective coefficients. So our product NO is going to be squared because it has a coefficient of 2, and it's going to be over our reactants N2 and O2, which are simply having a coefficient of 1, so they're raised to the first power. Now plugging in the mathematical expressions which we solved for using our ice chart, we know that NO concentration is going to be 2x, and that's going to be raised to the second power. And our N2 and O2 concentrations were the same. They were both 0.200 minus x. So for simplicity, we're just going to write that expression once and square that expression. And remember, we can set this equal to our Kc value, which is 0.10. Now actually, I see a way in which we can simplify this expression by not having to use the quadratic formula. That's because our numerator and denominator are both squared. So that means we can take the square root of both sides and then be able to solve for x without using the quadratic formula. So like I stated, taking the square root of both sides, that's going to give us the square root of 0.10, which is equal to 0.316, is going to be equivalent to just 2x over 0.200 minus x. So now this is a little bit simpler in terms of solving for x. We can multiply by the denominator on both sides, giving us that 0.063 minus 0.316x is equal to 2x, and by adding 0.0316x to both sides, we're combining like terms. So that leads us to say that 0.063 is equal to 2.316x, and dividing by 2.316 on both sides to isolate our variable, we get that x is equal to 0.0227 molarity. Now remember, this isn't going to be the final answer to the question because we were asked to find the equilibrium concentrations of the reactants and products at this temperature. So the equilibrium concentrations of N2 is equal to the concentration of O2, which is going to be 0.200 minus this x value that we just solved for. So the concentrations of our reactants N2 and O2 are going to be equal to 0.173 molarity once we plug x into this expression, and the concentration of our product NO is equal to 2 times this x value. So plugging in x, we get that this equilibrium concentration is equal to 0.054 molarity. So overall in this video, we learned how to utilize ice charts when we only know the initial concentrations of reactants and the equilibrium constant, but we would like to know the equilibrium concentrations of the reactants and products of the reaction. Sometimes we're able to assume that x is small, which can make solving for x a little simpler. Other times we might need to use the quadratic formula in order to solve.